Alright, what is going on YouTube? Today we are doing another LeetCode medium problem called top k frequent elements. I'm going to be doing this problem in C++ as always. So let's get right into the problem. So we're given an integer array, nums, and an integer k, and we need to return the k most frequent elements. So our answer can be given in any order. So just to look at the IO here to get a little bit of an idea of what's happening. So we're given this integer array nums, and we're given this integer k, which corresponds to like the top most frequent elements they want us to return. So just by looking at this array, we can see that 1 occurs 3 times. We can see 2 occurs twice, 3 occurs once. So obviously, 1 and 2 are occurring the top 2 most frequently. So you just return an array containing 1 and 2. And then for this example, it's even more straightforward. There's one element here. They want you to return the, top 1 element. So you just return an array containing 1. So as far as constraints go, we can see that k is going to be minimum 1. So k is never going to be like 0. So you're always going to have like at least 1 element to return. Presumably, also the number of the unique elements in the array is like the upper bound for k. So k is never going to be greater than the size of the array, which is nice. It helps simplify some of the thought that goes around planning for those edge cases. So yeah, let's just get right into this. So straight away, we can see that this array is sorted, but like the arrays they give us aren't necessarily going to be sorted. But like, you can kind of imagine like for a naive approach, like utilizing a sorted array to help like develop an algorithm to return the top most frequent elements. I've also seen people use priority queues and heaps for this problem, but nevertheless, if you're using a sorted an approach that relies on sorting the array, the best time complexity you can get is going to be so let's say sort the array. The best time complexity you can get is going to be big O of n log n, because sorting algorithms in programming languages are generally n log n runtime. It's like as fast as they can get. But we could do even better than this with bucket sort. So and that's the optimal approach. So if we solve this with bucket sort, we can get a time complexity that's linear. So that's obviously better. So time complexity big O of n is obviously better than time complexity big O n log n. So that's pretty much the key here. It's bucket sort. So I'll go ahead and start implementing this. So we're going to do an unordered map where the key is the value of the element, and the value, well, let's not do word soup here. I'll try to explain this a little better. So we're basically going to be storing the frequencies of the elements in a hash map. So in a hash table. So the key is going to be the element, and then the value is the frequency at which that element occurs in the array. So like the key 1 would have a value 3 for this, and the key 2 would have a value 2, the key 3 would have a value 1. So hopefully that makes sense. And then the way to populate that array is to literally just do a for loop. So for int num in nums, and then basically, at the map at that key, at the map at that element, we want to increment to start counting those frequencies up. Okay, so once you do that, we can now separate elements into buckets depending on their frequency. So the buckets are going to get set up like this. So we're going to do a vector of ints, and I'm just going to call that buckets. And how many buckets do we want? Well, we need a bucket for each possible frequency, and we can have frequencies up to as much as there are elements in nums. So the size, so the number of buckets we need is going to be nums.size plus 1, because arrays are 0 indexed. And then to populate those buckets, we're just going to iterate through the map that we just populated, the frequency map. So I'll use auto here. So for each element x in the map, we're basically going to say buckets at that frequency. So, and the frequency is going to be denoted by x.second, how we, it's what we just did up here. The value is the frequency, so x.second. And then we can basically push back x.first. So we're basically just adding this element into the bucket of the corresponding frequency. And then once we do that, now we have all of our buckets. We basically just need to go through those buckets and then, return the top k elements. We basically have solved the problem at this point for the most part. There's one more loop we need to write, but I'm just going to declare a vector for our result. Our result does need to be returned as a vector, so making that there. And then I'm going to use a C-style loop to iterate backwards through those buckets since we're returning the top most frequent elements. So int I is going to be buckets dot size plus 1, or that's actually going to be minus 1, because arrays, again, 0 indexing. And we're going to want to decrement I. And how long do we want to do that for is the question, the final question now. We basically want to continuously, add elements to res while res is less than, or the size of the result is less than k. And then, so basically that's going to allow us to iterate through each bucket, and then we're going to stop iterating as soon as, our result array reaches size k. So at each bucket, we want to iterate through the numbers in that bucket. So for num and buckets I, because that's like the bucket we're going to be at, if you imagine like a single iteration of this outer loop, right? We're looking at buckets I, we're iterating through those nums, and then we're going to push that num into our result array. So push back num. Okay, so that should pretty much be the answer there. No buckets, yes. Okay, and we can return res at the end of all that. Okay, now let's see if there are any bugs in this code. It doesn't look like it. Let me go over the space complexity too. So the space complexity for this problem is going to be linear with respect to the size of nums. Because it's linear because we have a map, potentially with as many elements as there are nums if they were all distinct. We also have buckets, which is going to correspond to the size of nums as well, because there can only be a certain number of frequencies. It's constricted by the size of nums. So anyways, time is linear, space is also linear. I'm going to go ahead and run this. And so past the initial test cases, let's submit to see our percentages. So beats 16.95%. That's really bad. So I'm just going to submit that again. That's 27%. Okay. This is not correct. This should be closer to like 90%. 62, getting better and better. Okay, I don't want to like submit this 40 times. Don't embarrass me now, LeetCode. 90. There we go. Fourth time's the charm. Okay, 98%. I don't know why it's like that. Maybe everybody codes the same solution. Who knows? But anyways, there we go. Yeah, beats 98%. Somehow it beats 98%, but it also beats 17%. Great job, LeetCode. But nevertheless, yeah, this is how you do. This is how you do top K frequent elements. So hopefully this helps. If you have any suggestions, please leave them in the comments below, and subscribe if you want to see more of these. And peace.